quickly introduce, welcome to our signal processing seminar. It's my great pleasure to introduce our speaker today, Professor Namrata Vaswani. So she is professor at the Iowa State University, and she's been very active in our signal processing community. I've been acting as the associate editor for the IEEE transactions on signal processing. She got the Signal Processing Society Best Paper Award last year. All right. And I've been working on a lot of problems in the interface between information processing and machine learning. The most important piece of information is Professor Vaswani is visiting CSL and UIUC as on her sabbatical this semester, and the office is in
156
CSLs. So she's very keen to establish any collaboration with student and faculty. So if you are interested in what you hear today, please stop by the office later and explore further connection. Right?
Thank you, Matt. So my talk is on online robust PCA. Before I proceed, I should mention that this talk is joint work with two of my graduate students, Chenlu Chu, who started this work, she graduated in 2013, and Ryan Lois, who's finishing what I should say is part one of this work, and he'll graduate very soon. Funded by NSF, other collaborators include Han and Professor Leslie Hogben on some of the work. Before I proceed to the main topic of the talk, let me give you guys a brief overview of my research because, as Min said, I'm looking for new collaborations. So, among other things, besides robust PCA, among other things that I worked on are various computer vision and pattern recognition problems. My PhD was computer vision. While doing that, I got interested in particle filtering algorithms, so I did that for a couple of years. After that, we designed some efficient particle filters for high-dimensional state spaces that would work, that won't be too slow for high-dimensional problems. More recently, I worked on recursive recovery of sparse signal sequences, or what could more popularly be known as online sparse matrix recovery. I'll give a brief overview of this in the next 2-3 slides. My current and ongoing work includes robust PCA and applications in video. And more recently, I'm out here actually with Srikanth and some others. We've been exploring applications to recommendation system design as well. So this is a 4-slide overview of my sparse recovery work. So how many people here are not familiar with sparse recovery or compressed sensing or either way? Everybody is. So motivating application, then I'll go through really fast on these 2 slides. Motivating application is MRI. Here's a commonly used image which is used to evaluate MR reconstruction algorithm. If you don't capture all the Fourier coefficients of this image, but capture only a few Fourier coefficients, in this particular case, you're taking a 256-point DFT along 22 radial lines. And then if you try to do what the MR scanner does, which is just inverse CFT, setting all the unobserved coefficients to 0, you get a very bad recovery. But if you use sparsity, you get exact recovery. Of course, this is not my example. This was Candace Romberg-Tau's example. More formally, this is the problem definition. So you have a sparse vector x with support size at most x, and you want to recover it from y. When the dimension of y is smaller than the dimension of x. And you could have noise, or even the noise-free case is not easy. Various ways to solve this problem. Applications. Most important applications are in projection imaging, where you don't acquire the image directly, but you acquire the Fourier coefficient or the radon transform, one coefficient at a time. Various ways to solve this. The most common one is L1 minimization. So instead of finding the sparsest vector x that satisfies your data constraint, you try to find the vector x that has the smallest L1 norm, amongst all those that satisfy your data constraint. Again, it was proved by Candace et al. That if the restricted isometry constant of the matrix A is small enough, essentially what that means is if you have enough number of rows, you have enough measurements, then the recovery error is bounded by a constant C times epsilon. I should mention the constant is obviously more than 1 because even in the noise-free case, it's a hard problem. RIC, for those that are not familiar, is the smallest real number that ensures that this inequality holds when restricted to sparse vector sets. So that's the notion. So if it wasn't restricted to sparse vectors S, then you would say A is an approximate isometry, but it's an approximate isometry when restricted to sparse vectors S. Okay. That was the introduction. This was the problem we looked at, which is recursive recovery problem. You have a time sequence of measurements y sub t, and you have a time sequence of sparse vectors x sub t that you would like to recover. And we use script, in our work we use n script n sub t to denote the support set of xt. And the goal is to recover xt recursively from y0 from all observations until the current time. The two key assumptions we exploit here are slow support change, which is to say that the support additions from the previous time to the current time are not too large, and same for the removals. And this is an assumption that we verified for MR image sequences, and it is true for at least certain types of MR image sequences. And then we also use slow signal value change or slow change of the non-zero entries to invalid. Based on this, we started this work with introducing what we call the Kalman filtered compressed sensing and its simplification that we call least squares compressed sensing. These were nice, and we were able to study at the LSCS algorithm as well, but it had a key limitation which was removed by our later work on modified CS. And let me give a brief idea of this. So here's the key idea. Once you actually reformulate this problem, the solution jumps at you. So you reformulate the problem as one of sparse recovery with partial support knowledge. And you use T to denote the support knowledge. So under this, once you formulate the problem this way, what modified CS tries to do is tries to find the vector x that is sparsest outside the set T amongst all vectors that satisfy the data constraint. Okay? So the idea, it would be even clearer if there was no delta E. So imagine for a moment that you did not have any extra entries in the set T. Your support of x was T union delta. You were told T, delta was unknown. Okay. Then what are you trying to solve? You're trying to find a vector x that is sparsest outside the set T, subject to the data constraint. Turns out the same idea works even if there's extra entries, because those entries would automatically turn out to be estimated as 0. And that's indeed what happens. You can show exact recovery in the noise-free case under a weaker RIP assumption. Assumption is weaker, of course, when support knowledge is accurate. So the set of missing entries and the set of extra entries is small compared to the support size. Under those assumptions, this is a weaker condition. For the noisy case, we are able to obtain time invariant bounds, again under realistic assumptions. And then we are also able to look at this and its extensions for applications in dynamic MRI. For those that are interested, I can show some of the results for this offline. If there is any questions on this part of the work, I can quickly answer them. Otherwise, I'll jump to the main part of the talk. Good. So that brings me to the main topic of today's talk, which is robust PCA. PCA,
How do you select this T? Actually, the partial formation of the travel. How do you select this T?
Oh, okay. So, sorry. Yeah, good question. Excellent question. So the idea was, so you have a recursive recovery problem. You recovered the signal at time t minus 1, get an estimate of its support, and that serves as a good predictor of the support at time. Right? And that's how you get the support knowledge T. For the first frame, you either use simple L1 minimization, or you can use other prior knowledge about your image. For example, so for most images, if you look at if they're wavelet sparse, then what is it called? The low frequency coefficient. What is the term for it? Not the scale coefficient. Essentially, the lowest frequency components of the image would be non-zero. So you could use that knowledge. Approximation. In wavelet, you probably know this. Approximation coefficients would be non-zero. So that set could form as your support knowledge T to start initially. Any other questions?
And it applies a sort of hysteresis or smoothness to the Kalman filtering that might not even otherwise exist. I mean, we have this problem in speech where if you do this minimization on a frame-wise basis, then the basis vectors that you choose in each frame are completely unrelated to the basis vectors of the previous frame, which is undesirable in most cases.
Okay, that's another point.
So you could actually impose some smoothness where it wasn't necessarily required by the problem, but where it's actually useful for implementation. I guess.
Okay, that's another way to look at it. So I was thinking more in terms of, does it satisfy, so the way we looked at it was, does this assumption hold for some real image sequences? We tested it, and turns out it did hold, and then, but that's another, and maybe we should talk more about this offline. I have a whole talk on this that I can run over with you later. But I was here for a colloquium some years back where I talked about this, so I figured I should talk about something else now.
Okay.
So, okay, so jumping into the main part of the talk, robust PCA. So PCA says that, assume that a lot of high dimensional data today lies in a much lower dimensional subspace. If that assumption is indeed true, a lot of people tell me that it is. Then PCA solves your problem because it says it helps you find a low dimensional subspace that best approximates your given data. If your data is noise-free or relatively noise-free, not small amounts of noise, then SVD solves it for you. One line of MATLAB code, you're done. Robust PCA, on the other hand, is a much harder problem because it's the problem of PCA in the presence of outliers. You don't know where the outliers occur, what they are, what their magnitude is. Again, it's a traditional problem studied for many years. Many useful heuristics have been proposed. Most popular among them is RSL by Dilatar and Black. More recently, in 2009, actually, this work came out of here. Yima, Candace, Wright, Lee, and Ma. Yima's group here posed robust PCA as a problem of separating a low-rank matrix L and a sparse matrix X from Y. The idea being that outlier is something that occurs occasionally. When it occurs, its magnitudes could be very large. So model it as a sparse vector, or a sparse matrix in this case. So here and on, I'll use this definition of robust PCA. So in particular, notice that if L or range of L is the quantity of interest, then it's a robust PCA problem. On the other hand, if you're going to recover L, you're also recovering X. So if X is the quantity of interest, you could interpret this as robust sparse recovery in structured noise L. Applications, there's many. A key application, again, since I come from a computer vision background, this is the application that appeals to me the most, is video analytics. So the idea here is xt, which is the tth column of the matrix X, is the foreground image, arranged as a 1D vector. L sub t is the background image, arranged as a 1D vector. The assumption is that the foreground consists of one or more moving objects, so it's a sparse image. The background is usually slowly changing, so at least from a static camera. So the resulting matrix, so if the background didn't change at all, the resulting matrix would be rank 1. If it's slowly changing, hopefully it's still a low rank matrix. Okay. Other applications include recommendation system design, where it's actually really a problem of robust PCA with missing entries. So there the idea is, suppose think of the Netflix problem. So L sub t is the vector of ratings of movies by user T. And the assumption is that user preferences are governed by only a few factors. That's why the matrix L is low rank. I don't know. Again, this is not data I've worked with, so I don't know how true this is. Candace et al. Says it is true. Given user, again, so the goal is to recover the matrix L in spite of outliers, which may be due to lazy or malicious users, and there could be missing entries because the user will not enter all the ratings for all the movies. And other potential applications people have looked at are in detecting anomalous connectivity patterns in either social networks or computer networks, as well as functional MRI-based brain activity detection or dynamic MRI-based region of interest detection, or there could be many others in speech, for example. So in recent work, Candace et al. Introduced, and then also Chandrasekharan et al. In parallel introduced what they called a convex optimization program called PCP, or Principal Components Pursuit, which solved this optimization problem right here. Here, star is the nuclear norm, 1 is the vector L1 norm. And they showed that under relatively simple assumptions, PCP will exactly recover X and L with high probability. And as far as we know, this is the first set of guarantees for a practical robust PCA approach, because they also demonstrated some applications in video. Since this work, there has been a lot of later work on batch robust PCA algorithms along with guarantees for it. Now, while batch methods are nice, they have some key disadvantages. One is they're slower, especially for online applications. Those might be memory intensive. You need to store the entire matrix in memory. And then in particular for this problem, there's a third disadvantage, which is that they do not allow infrequent or slow support change of the columns of X. Whereas in video, many of these applications, this is a common problem, because what happens is if the support changes slowly, imagine the extreme case where the support never changes, and the entries also never change, then the matrix X itself would be low rank. So it becomes difficult to separate a low rank matrix from another low rank matrix, unless you use something extra, right? So on the other hand, this is an issue that occurs in a lot of practical applications. In video, you could have foreground objects that are moving, but could occasionally be static. fMRI, the activated brain region, again, changes only a little from frame to frame. Same problem with network anomaly detection. Let me show a quick example of video where this does occur. So in the leftmost column, I show an original video sequence. This consists of, the background consists of moving curtains. The foreground consists of a person coming in, standing, writing on the board and talking, and then walking back out. Another person coming in doing the same thing. So the person is moving slowly and is also occasionally static. Okay. In this particular case, PCP, here I'm showing background recovery, so you shouldn't see the person in the background. PCP confuses the person for the background because it's so slowly moving. Same with RSL, which is another batch technique. There's the proposed algorithm, which is an online method, but uses extra assumptions, I should say. Otherwise, an online method would not do this. Is able to separate the background correctly. Grasta is another online method that appeared later. I'll talk about this. Is also able to do well at least for the first couple of frames. Same thing, of course, with foreground recovery. If foreground is correct, but if background is correct, foreground will be correct. I'll come to this experiment in detail later, but right now the point was just to motivate that this occurs. Okay, so why is what I call, that's why I put online in quotes, because when we formulate the online problem, we introduce some extra assumptions which help us actually remove a key disadvantage of the batch techniques. So we use two extra things. First is we assume that we have an initial short sequence of outlier-free data, which is easy. For video, that means you have an initial short sequence of background-only image sequences. And then after, say, t equal to t0, you could have outliers or you could not have outliers. It doesn't matter. xt, the support of xt could be of size 0, so then you don't have outliers. The other assumption we used is that the LTs lie in a slowly changing low-dimensional subspace. And this is what I mean by slowly changing. Well, I'll come to this later again. And then, of course, we also need some changes in the support for us to see behind, because when the subspace is changing, we need to recover it. So we need to see behind the foreground to be able to recover the background. So we need some support changes of xt. And then we need an assumption on the left singular vectors of this matrix. Roughly speaking, what this means is the background image changes should be more global in nature, should not be sparse. And then the goal is to recursively estimate x sub t, L sub t, and the range of the matrix L sub t. Okay. As I said, outlier-free sequence, the key assumption, people might look at it as a limitation, but this is often valid for real data. For video, it's easy. Functional MRI, also it's relatively easy. When it's not easy, for example, recommendation system design, it's not easy to get this. You could initialize with any batch method. You could use PCP or any batch method to initialize and then proceed with the proposed approach. I should also mention that I'm going to talk about, for ease of understanding, only the full sampled case, which itself is hard. But the ideas extend almost directly to the undersampled case, which is relevant to MRI applications. In terms of related work, there is a lot of work on the batch problem, some work on the recursive robust PCA algorithms, almost no work on the guarantees. We have some work that's upcoming in, I guess, 2015. Now I move on to the main part, which is the algorithm. Before I do that, is there any questions? I I have a habit to speak fast, so it's good if people stop me between work in 20 minutes. If nobody asks me questions. Okay, good. So either nothing is making sense or everything is making sense. Hopefully it's the latter. So yeah, I use a few definitions. Whenever I say P is a basis matrix, I mean that P consists of orthonormal columns, mutually orthonormal columns. I use the term estimate P. What I mean is estimate the range of the columns of P, which is the subspace spanned by the columns of P. Whenever I say P hat is an accurate estimate of P, what I really mean is the subspace recovery, the subspace error between the subspaces spanned by P and P hat is small. In quantified that way, standard measure for subspace error. So here is the key idea of the algorithm. So notice that y sub t is x sub t plus L sub t. And I said L sub t can be written as a tall matrix P times a short vector L. So assume for a moment that, just for understanding the key idea, assume for a moment that P is known. Then how would you, then it's an easy problem. How would you recover L and X? Any ideas? So if I had this problem, and suppose for a moment I told you P sub t.
Project away.
Right, exactly. So if you knew P sub t, you would project away LT by projecting YT perpendicular to the subspace span by P sub t. That would nullify L sub t, but would give me projected measurements of X sub t. The question then is, as long as you can show that you can recover the sparse vector X sub t from these projected measurements, you're done. Okay? And this is the key idea that we use to develop the algorithm. We don't, of course, have P sub t, but we know P0 hat, which is an accurate estimate of P0. May even be an exact estimate if you truly knew L1 through LT0. At time t, suppose for a moment that you have access to the previous subspace, you have P hat t minus 1 available to you. Then you do exactly what Yoram just said. You project perpendicular to P hat t minus 1 to get y tilde t. Now, this would not, now PT could be different from P hat t minus 1, but because of the slow subspace assumption, this would result in only small noise beta t. And then I'm left with trying to solve this sparse recovery problem in small noise, which is a standard easy problem to solve. Pick your favorite recovery technique. For simplicity, we used L1 minimization, followed by simple support-based thresholding, followed by least squares to get xt, but you could use any other approach and that will work. I should mention here that notice that phi looks like a square matrix, but it's rank deficient, so you cannot just invert phi and get x. Okay? So I've had this question in previous talks, so I can clarify it. The denseness, the reason, now the second question that comes to mind is why is it true that you can recover x from y tilde? Because the denseness assumption on the columns of P ensures that you can actually do this. And then once you can recover x accurately, you can recover L accurately. And then most of the work goes into updating the subspace every alpha frames via a modification of standard PCA that we call projection PCA. I'll explain why that's needed. So is the overall idea?
So you note T naught, that's assumed to be known.
It's assumed. Yeah. You assume that you have a short sequence, you know how many frames that definitely don't contain the outlier or the foreground. Yeah, you need to.
So I'm sorry if this is naive, but projecting onto the orthogonal subspace then doesn't necessarily having capital P sub t be dense, then does that allow you to guarantee that that just like an L1 minimization over y tilde t results in the sparsest possible xt? It basically goes back to Canvas's proof then at that point.
That point, yes.
Okay.
So most of the effort is in this part, and I'm coming to that in the next two slides.
Okay.
Why this is a not so easy problem to study. The first thought would be, okay, combine Canvas's proof with the standard result for PCA and you should be done. Next two slides I'll explain why that's not the case.
Okay.
So, okay, first to answer Mark's question, this is exactly right. Slow subspace change ensures the noise beta t seen by my CS step or my sparse recovery step is small. The denseness assumption on the columns of PT ensures that the restricted isometry constant of this matrix P can be bounded by a small value. So this part is not too hard to see. that this is equal to this, and then the rest follows, and this is the denseness assumption we use, which is, if you're familiar with Candace et al. Paper, you follow this. Essentially, this says that the 2 norm of any row of PT minus 1 is small. So that, because the columns are anyway unit norm, this ensures that all entries of PT minus 1 are small. So none of them is 0, basically. And that can be used to, and then you can show that the restricted isometry constant of I minus PP transpose is actually equal to this quantity, and then this quantity is bounded by this, which is, again, just triangular inequality. And then, because you're using the fact that P hat T minus 1 is an accurate estimate of PT minus 1, that's where the second term comes from. Okay? Now, these two facts, so RIC small, beta small, ensure, result of Candace ensures that X is accurately recovered, which means L is accurate. And then, you cannot use standard PCA. Most of the work is going into this part. You cannot use standard PCA because notice that the error E between L hat and L is correlated with LT itself, right? Why? Because this error is equal to this error. And this error, xt minus x hat t, depends on beta t, which is the noise seen by the sparse recovery step. And if you notice, beta t itself is phi times LC. So the error actually linearly depends on, roughly speaking, this error ET linearly depends on L sub t, right? Which is a problem. All standard PCA results assume that the noise seen by your observed data vector is independent, or at least uncorrelated with the true data vector, right? Let me explain that a little more. So let's assume we want to try to use standard PCA, and ET is defined as above. So you would like to, if you knew the LTs, you would like to compute the eigenvectors of this matrix. But all you have is access to this matrix, so you can see the eigenvectors of this matrix. So the perturbation between these two matrices can be written as a sum of 3 terms just by using the definition of LT. Now, when ET and LT are uncorrelated, and if one of them, or usually both of them, are assumed to be zero mean, you can argue by law of large numbers that these two terms will be close to 0 with high probability. Okay? That's what standard PCA results usually assume. ET and LT are uncorrelated. And then all you're saying is, if the error is small, if the noise is small in your observed data, everything is nice. In reprox, this is not the case. ET is correlated with LT. So the first two terms are actually the dominant terms. And that becomes a problem specifically when the condition number of this matrix is large, right? Because when you try to bound the subspace recovery error using a standard result, which is called the sine theta theorem, the bound depends critically on the 2 norm of the perturbation, which is this matrix, the difference matrix, divided by the minimum eigenvalue. Okay, so if that ratio is large, either you can't even, you can of course apply the sine theta theorem only when the denominator is positive. Either you can't even apply it, or you make it a trivial bound that's more than 1. Okay?
The 2 norm meaning spectral norm?
Mm-hmm. Yeah, 2 norm, whenever I say 2 norm of a matrix, I mean the spectral norm or the induced 2 norm. Questions? Okay.
So in fact, you have the, I mean, the previous slide claimed that E is phi times L. Is that, am I remembering that correctly?
No. E, that was beta.
Oh, I'm sorry.
No.
Beta is
the
phi.
beta was phi times L.
Yeah, okay.
And E is actually the error between x hat t and xt.
Okay.
And remember, I'm doing alpha minimization followed by support recovery followed by a least square step, which is why the error between x and x hat t eventually almost linearly, or actually linearly, depends on beta. Okay. Which makes life easier, but it also gives us easy expressions for ET and LT to work. For ET to work. Yeah.
So then you want to find that basis, essentially. Is that right? You want to find, if ET is that linearly proportional to LT, you want to find the basis of
It's not as, I'll get to the, if I can, I'll get to the proof outline and I'll explain to you, and I can explain that to you. No, this is not an easy, at least the way we have approached it, unless there is some trivial way that we haven't seen. It's not an easy problem showing why projection PCA works. I'll also come to the projection PCA algorithm, but towards the very end. let me get through first the correctness result. So this is what we can say in English. For most videos, which is to say with high probability, what we can show is this. We can show that the region occupied by the foreground objects is exactly recovered. I mean, the support of xt is exactly recovered. The foreground and background images each are accurately recovered with error bounded by a time invariant and small constant. The background subspace recovery error decays to a small value within a short delay of a subspace change time. I'll tell you what that means. Under the following assumptions, you need this initial training sequence, or you need an initial estimate via PCP. Then you also need the LTs to lie in a slowly changing low dimensional subspace, and we have a specific model for it for the purpose of the result. You need the background changes to be dense, which means there should be global changes. Background changes with respect to the mean should not be sparse. And then you need some foreground motion, although we are able to get away with a much weaker assumption on foreground motion as compared to what the batch methods need. And let me come to the details now. So here is what we need for support change. Of course, the best case even for our approach is all support sets being mutually disjoint. Alternatively, we also allow, think of, these are again examples, the most general cases of course in our paper. Consider a 1D object of length s that moves at least once every so many frames. And when it moves, it needs to move by a fraction of s, where s is the maximum support size. And this again satisfies our model under a certain assumption on s. And then we also allow what we call slow motion, which is an object moving by at least 1 pixel at every frame. But then we need a tighter bound on s. So here's the visual description of the three models. This is the best case. Supports mutually disjoint at all times. Change it every time and mutually disjoint. An object that is constant, does not move for a while, then moves, then does not move for a while, then moves. But when it moves, it should move by a fraction of s. So here I show the example where it moves by at least s over 2, but s over 10 is okay too. And then this is the slow moving object case. Okay. And I'm talking about objects because I'm thinking of video as my motivating application, but in all of these you could have random permutation of the pixels and everything would still work. Okay. That's the support change, what we need on support change. On LTs, what we need is, in the simple version of the result, we need LTs to be zero mean bounded and mutually independent random variables. We're able to get rid of the mutual independence assumption later. With a covariance matrix sigma t that has this form. So essentially, the covariance matrix is slow changing in the following fashion. The subspace p sub t is constant for a while, then changes. And when it changes by adding new directions to the subspace and removing more directions. And by slow change, I mean two things. The eigenvalues along the new directions are small for some time for d frames after the change. That's the main thing we need. And the second main thing we need is the subspace should not change very often. The subspace of LT, or if you would rather prefer the subspace of the column subspace of sigma t, doesn't matter. It's equivalent. Almost surely equivalent. Okay, so this is what we need for subspace change. Then let me define a few quantities which I'll use in the result next. So I use C, most important is C, which is the maximum number of new directions added. And then lambda plus is the maximum eigenvalue along any direction at any time. And R is the maximum rank. And I should mention that, yeah, there's a total of capital J changes, so you can't have infinite number of changes. Even though the time length of the sequence could be infinite, you need a finite number of subspace changes, just because it's a high probability result. Otherwise, the probability would keep start going to 0. Okay, under this assumption, we can show the following. Pick a zeta that's small enough, and this depends on lambda plus. If certain algorithm parameters are appropriately set, which have long expressions, I can show them to whoever is interested later. If these conditions hold, you need accurate initial knowledge. You need slow subspace change, which means two things. First is that the projection of LT along the new directions is small for the first d frames after the change. Technically, it means these things. And second is that the delay between change times is large enough. This this delay is larger than this quantity, equals to alpha. Then you need a denseness assumption on subspace basis matrices, which is this. And then you need that the support of xt has some changes. The support of xt is bounded by S and changes enough. So, for example, this will work. Okay. And then under these four assumptions, what we can show is that with probability at least so much, everything is nice. The support is exactly recovered, xt and lt are accurately recovered, and the subspace recovery error, every time there's a subspace change, obviously the recovery error is 1. But then within a finite delay, it decays to a small constant times zeta. And zeta, remember from the previous slide, was a very small constant that we picked.
So where does the exponent 10 come from?
N to the minus 10?
N to the 10 on top. Where does it come from? Minus 10.
N to the, oh, where does it come from?
Yeah.
Okay, that's a complicated one. It comes from trying to match the PCP results. We got the same exponent. You could get another result with N to the minus 3, and all that would change would be the value of the constant alpha. Right. So what we wanted was decay with, so the probability of error, probability of the bad event should go to 0 polynomially. You can pick n squared and your alpha required would be smaller. We picked n to the minus 10 because a lot of recent papers pick n to the minus 10. Right? So it comes from analyzing the projection PCS step and ensuring that that holds with high probability. Everything is nice there with high probability. So there's nothing sacrosanct about 10. I could pick 20.
But conversely, let's say if we give a typical video, right? So we can take a particular resolutions. If we know the foreground, we know the background.
Mm-hmm.
How do you plug in to get those numbers, and what the probability can you find out that the algorithm will succeed?
Oh,
Because everything here is some number, right? So can you quantify more accurately? Let's say if you give a video, what is this number? Typical number.
No. So let me be clear. The expressions for alpha that I get are much larger than the alpha that I would use on my real experiments. So I haven't given you the expression for alpha. I have it at the end of my slide. So alpha is the number of frames I use for a given PCA step. The expression that I get for the theorem to hold is very, very large. Okay.
How large?
I've tried to, my student has tried to compute it. Where is it? It's at the end of my time. Here is your alpha, okay, where C is this constant right here. So you need to know lambda minus, which is the minimum, lambda 0 minus actually, which is the minimum eigenvalue of your training data. You need to know C. C psi is given by this quantity. So yes, you could, if you gave me a video, yes, in principle, I could compute these values for you, but they will be so large that I may not have such a long video sequence.
Very good. Just
Yeah.
get a rough idea. So how long? I mean, the typical.
So
severe
if you're
video,
asking me, so for
how many
experimental
frames would you
data,
use?
so for experiments that I showed you, and I have more experiments, alpha, k, all these parameters are picked differently from how they're picked here. Right, so there alpha equal to 50 or 100 suffices for my experiments. Right?
That's empirical.
That's empirically, it suffices for the type of videos we have experimented.
But the theorem, you know, how much they guarantee?
If you look at these numbers, there's 20 squared and 26 squared.
This already is
Like,
like.
the number is bigger than 1, so
this
you're
one,
going to get
yeah.
a few million frames maybe.
And this ratio is more than 1, so you get, yeah, maybe a few million at least. Yeah, that's true. So, and the k, the number of times you need to run your projection PCA step to get your error below whatever constant you wanted, it's always be like 22,000 any which way. So these numbers are only for the, just like with even the PCP result, if you compute the rank bounds, try computing the rank bounds, you'll get very, very small rank bounds.
So
Even though in theory, you know, the result scales almost linearly with rank and almost linearly with, so rank scales almost linearly with the matrix size, but
But
the actual
this is
concept.
typical of RIP analysis.
They're-
It's very conservative.
they're typical of RIP analysis, they're typical of applying matrix hopping and some of the other results too. So yeah, they won't be. Yeah. Okay, so the key point I should mention is that, so again, when I said I can analyze an algorithm for which I also have experiments, I just meant that in experiments the parameters were set in a different fashion compared to how they were set in the theorem. Yeah, the key point to notice here is that we don't have a bound on lambda plus or gamma. Lambda plus was the maximum eigenvalue of any of the covariance matrix of LT. So, and gamma was the max, essentially proportional to the maximum entry of any LT. So essentially what this says is you could think of this result as a result for sparse recovery in large but structured noise.
Where does S go? Which of these are affected by S, the sparsity? So, you have 1% versus 10% sparsity.
Here. The sparsity and the denseness assumption actually are coupled together.
Okay.
So this is really not, I'm calling this denseness because it's related to denseness of this quantity. But this is putting a bound on denseness, rank, and sparsity, all at the same time. Okay, good question. And then details are in, actually this is the best preprint to look at. The other two are also okay, but they're not. So to mention, so we have a correctness result for online robust PCA. Online is useful because it's faster and it needs less storage. Again, up to order calculations, we need order n log n. Storage instead of order n times Tmax, where Tmax is the number of columns in your matrix. We can again, up to order computations, allow significantly more correlated support changes than PCP. So you can show that the fraction of non-zeros per row of X allowed by reprox is order 1, whereas it's order 1 over rank of L for PCP. Or, of course, the result of Candace et al. Requires the support to be uniformly random, so that's even stronger. Okay? And then we need new proof techniques for this problem for two reasons, because all existing work is for batch methods, and because previous PCA results require the error to be uncorrelated with LT, whereas that's why there is work to be done in the proof. Of course, that said, there's a lot of limitations. First of all, our algorithm needs to set algorithm parameters in a certain way. In particular, it needs knowledge of these two model parameters to do that. And then the algorithm parameters that we set are not very useful in practice. So when we experiment with the algorithm, we set them differently. We need a tighter bound on rank and sparsity compared to PCP. So if you're familiar with the PCP result, it allows linear sparsity and almost linear rank in N, whereas we allow sparsity that we allow is almost linear, but the rank bound we need is much tighter. We have ongoing work that removes this limitation actually, but needs one extra assumption. I'll talk about this in the end. We need extra assumptions. Which is why we have some advantages. Initial subspace knowledge, slow subspace change, and a mutually independent assumption of the LTs, which really models independent background variations around a fixed mean. And then, of course, again, this is an ongoing work. We are able to replace this by a more practical, more valid autoregressive model.
So if you have panning or zooming off the camera, that would not apply because you fail those independent assumptions.
Well, not just independence, you would not even be low rank. Forget independence. Independence can be replaced fairly easily by an autoregressive model, so that would apply for a lot of real backgrounds. But you would fail anyway for a panning or zooming camera because of motion. So.
Well, it depends how fast you pan it zoom.
No, but if you look at even a little bit of pan, if you look at background images arranged into a matrix, they would no longer be as low rank as they were if you weren't panning. So that's actually an open question that my student is looking at for video sequences. That's an important question, is how do you deal with moving cameras? So one approach we're looking at is, can you estimate the motion to ensure that the resulting background image matrix is low rank? But that, again, that works beautifully for simulated data, but fails for real data for a lot of other reasons, which I can talk to you offline about. And yeah.
how do you exploit the fact that the support of X changes but in a structured way, right? So is there a way to exploit that?
That's where we exploit in the proof.
Hmm?
That's what we exploit. You mean exploit in the algorithm itself? Yes, we can.
Okay. But how could you do that?
Well, one simple way that we've already explored is using our older work on modified CS.
Okay.
So use the fact that the support, if the support indeed changes slowly over time, and if you wanted to exploit it, instead of using simple L1 minimization, you could use modified CS, which uses the previous support knowledge as a predictor.
But so you make implicit assumptions for the way it changes over time, right?
Yeah, so what was your question?
Well, I'm wondering what exactly those assumptions are. So there must be some homogeneity assumptions. So it's like in compressive sensing, if you look at not just sparsity, as counting the number of non-zero components, but assuming you have a certain structure, you have quite different algorithms and quite different bounds, right? And so here, and the bounds then depend on the structure of the support, right?
Okay, so what you're saying, yes, so you're right. So instead of using simple L1 and recovery, doing a frame-by-frame recovery, you could use all the work from structured sparsity.
Yes.
And you could, with simple modifications, apply all the results for that work.
Is it that simple?
It is very simple, yes.
Okay.
It's a question of, the algorithm, again, my student this semester, one of my students is looking at some of that.
Mm-hmm.
It doesn't apply as easily to video. So even those works, they are nice in theory, but they don't always apply for model-based sparsity, for example. So, yeah, and let me get to the proof outline if I still have time. If your question was, how do you use I assumed a certain structure on support change already, that the support doesn't change, support changes at least every so many frames. I'll come to why that's needed for the proof in a second. So some generalizations are, there's a direct application to online matrix completion because it's actually a simplification of this problem where the support of your sparse vector, you can think of it as known. Easy extension to the undersampled case. Independence assumption can be relaxed by essentially replacing the matrix sorting by the matrix assuma and some other changes. And then we are analyzing what we call reprox with deletion that also deletes directions, the estimate directions from the subspace. This needs one extra assumption, but then it relaxes the denseness requirement a lot. And it allows it actually allows linear rank, which is nice. Extension to matrix completion is easy and not really interesting. Okay. Now let me come to your bill. We'll take 1 minute to give the proof out, 2 minutes to give the proof outline, and another 2 minutes to show experiments. So here's the complete algorithm, which I had skipped this part earlier. This step comes in the next slide. So here's what I mean by projection PCA. So I'll use the model to explain the idea, although the same projection PCA algorithm also works for videos where there isn't a model actually. So let's say Tj is where the subspace changed. Assume for a moment that I'm able to estimate this change within a short delay, T hat j. Then what I do is the following. I take at T hat j plus alpha, I take alpha frames, at T hat j plus alpha, I look at L hat t's for the last alpha frames, and I project perpendicular to the previous estimate of the subspace, estimate of the previous subspace. So I assume that before Tj I have an accurate estimate of the previous subspace. Right? Now, again, forget about the deleted direction, assume for simplicity that Pt can be written as just Pj minus 1 and some new directions. I know Pj minus 1 very well. So what I'm doing here is, I'm taking the last alpha L hat t's, projecting perpendicular to P hat j minus 1, and then computing the SVD, retaining top left singular vectors above a threshold. And that gives me my first estimate of the new direction, which I call P hat mu 1. Now for the next alpha frames, my P hat t is a better estimate of Pt because I have an estimate of the new directions. So my compressed sensing step or sparse recovery step will be better, which means my LT will be recovered better. Which means that T hat j plus 2 alpha, in these alpha frames, I have a better estimate of the LTs. I again do the same thing. I take the last alpha estimates of LT, project perpendicular to P hat j minus 1, which was my subspace estimate from here, and again do SVD. That hopefully gives me a second and better estimate of P and T. I'm doing this until I get a good enough estimate. Do this k times. That's really the algorithm. For detecting subspace change, I do exactly the same thing. I take alpha frames at a time, project perpendicular to this, and keep checking if the maximum singular value is large enough or not. Okay? Now here's the key idea, which maybe if that was Pierre's question, then that answered it. So before the first projection PCA step, notice that PT is a P star and a P nu. Let's say star denotes existing directions. P hat doesn't have a P nu. So beta T at this point is the largest. So ET is the largest. But it's still not too large because of slow subspace change. And the second important thing to notice is ET is sparse. Right? ET you can show is actually supported on, under certain assumptions, is supported on T sub T. And then I have a certain model on T sub T. That helps ensure that my first estimate of P nu is accurate enough. I just need this constant to be anything more than 1 and I'm okay. Okay, for the first estimate. Okay? For the next alpha frames, PT is this, but I have a better estimate of P hat T minus 1 because I have an estimate of the new directions. Now beta T is smaller, and so ET will be smaller. And then again, the key is that ET is smaller, but also the fact that ET is sparse and supported on T. That's the key that helps us get the complete proof. And that's what actually is. And then at T hat J plus 2 alpha, you get a better estimate because of this. And continue this way, you can actually show this kind of a bound under certain assumptions, certain things set a certain way. And that's where, in setting this, you need to set your alpha, and you set your alpha to ensure that this holds with, okay, this should be with high probability. If you want a probability 1 minus n to the minus 10, you set alpha in a particular way. So that's where alpha comes in. To do this, to do exactly what I said, you use essentially the Candice result for the sparse recovery step, sin theta theorem followed by matrix sorting. And in particular, to apply matrix sorting in a nice way, we use a particular lemma that we prove for matrices that are of this form. So that are supported on T sub T, that are essentially block sparse, I should say, with, or I should say block banded. Block banded is the correct term. So they have blocks. So for these types of matrices, the 2 norm of these types of matrices, which are not full matrices, is much smaller than the 2 norm of a general matrix. And that's the key that helps us get to it. Okay? And then you use Cauchy-Schwarz matrices. I can of course run over this in detail for people that offline, because this is script. Here are some experiments, and I guess I will stop with this. So this is some experiments with simulated data, or partially simulated data. We had a real background, which consisted of moving lake waters, and we simulated foreground on top of it. We made a block object move slowly over time. And then this allowed us to do Monte Carlo and compute recovery error, average recovery errors. So y-axis in this plot is time. X-axis is the normalized mean squared error in recovering the, I guess, either the foreground or the background, I forget. The red methods are the online methods. Red circles is reprox, which is the proposed method. And the squares is Grasta, which is the work of Balzano et al. From CVPR 2012. Our work actually appeared in Allerton 2010. And then this is an older algorithm, which again, what you see is the other recursive algorithms start working but later fail. PCP does not work because, again, slow moving program. RSL works to some extent. RSL is actually not too bad, but again, doesn't work as well. Here is the...
So you compare only this method with robust PCA frames? Right?
Only robust PCA based.
Right.
Sorry, yes.
But here you have the background, right? You can very simple minded just subtract the image to the background, and you take any pixel above certain threshold.
Yes.
You know the statistic?
Yes, I have, yeah. So that would recover only the foreground, and I have those comparisons on my student's webpage. My student has those comparisons. I don't have them in this
But if
particular.
you have a foreground, you have a background, right?
No, but
you know the background.
Sorry?
You know the background initially.
You know the mean background, but background can change. You know the mean and you know the but slowly.
Yeah.
So you can what you can do what is standard in computer vision, which is called background subtraction, which is essentially either subtract a mean background image or sometimes do frame differencing and threshold.
So how that very simple method would work?
That doesn't, again, I don't have the plot here, but it works to a certain extent, but doesn't always work. Because remember what we are saying is background could lie in a low dimensional subspace, but the actual changes along that subspace could be pretty large, right? So as long as video does satisfy that assumption, our algorithm will work, but background subtraction would not work, because it depends on actual pixel values being small over time. See what I mean?
So
And
what cases
if I can connect to the internet, I can show you some of those results that were on Chenlu's page. And the other thing, of course, is that, okay, I can show those to you offline. No, this doesn't, I think I need to enter some information. But that doesn't do as well because, there could be significant changes in the background as long as it lies in a lower dimensional subspace. Right? Even though when I motivated the algorithm, I said, background is slowly changing, so it will do this.
Because more of these methods, they update the background, it slowly change, you can learn the mean and the mean can be updated.
Okay, that's what you mentioned, what OpenCV has. I have not looked at those methods enough to answer your question.
So this is typical, you update, so the mean is 50%, the mean and 50% from the current latest frame. So if things slowly change, you can just have local.
No, but what I'm saying is that if you recover the foreground, so if you're recovering the foreground by subtraction, you're actually recovering the foreground pixels. You're not actually seeing the background behind it. So you are using some kind of interpolation to fill in the background, right? So what these background updating methods, actually now I remember at least, I've seen some of the work from CVPR 2008 or 2009. What some of these methods, at least there's work from UCSD, Vasconcelos's group. What they do is they learn a complicated model on background change. Instead of me learning a model that says background lies in a low dimensional subspace and I store the principal components of that subspace, they learn some model. They sometimes assume a Gaussian mixture on background change. Use training data to learn that Gaussian mixture.
Well, here I think the very simple, just one background and you keep updating it because the things move across, so you maintain.
No, because the point I'm getting at is here when I say foreground recovery, all the time what I'm really recovering is not the foreground. I'm recovering my x of t is actually the difference between foreground and background on the foreground. Right? On the support. So what I recover is not quite the foreground by the algorithm. I recover the difference between the foreground and background supported on the foreground support. Okay? So because of that, by subtraction, I'm also able to recover the background. Whereas any technique for background subtraction only extracts out the foreground support. Just because I know this region correctly, I cannot figure out what's behind it, right?
No, you can learn that. You have the initial background, so the algorithm would be clever enough that when you know this foreground, you don't update that. And then when the things move away, then you have a new foreground, you keep updating.
Yeah, so then you have another model instead of me putting a low rank model on background change, slowly changing low dimensional subspace model. You have other models on background change.
So intuitively, I just wonder.
So you do need some model on
you
you need an initial training data and you need some model on background change for it to work. One
And so
reason.
your model is that the background is a low rank matrix.
Yeah, background is a low rank matrix and slowly changing. A slowly changing subspace assumption, which.
We also know the initial background.
No, we don't know. We know an initial short sequence only to estimate the background subspace. And or we could use PCP to estimate the initial background.
So you have initially the average background as well as sort of the subspace of which the background is
Precisely.
varying over the
Precisely. All you need
frames.
is, yeah,
Yeah, and then you update that subspace as you go.
you update that subspace as you right.
Yes,
So
I think trying to
it's
send
a
the
model on
assumptions.
subspace change.
Mhm.
There's other work that uses Gaussian mixture models amongst those, at least some of the stuff I've seen from, this is older work, I haven't seen a lot of the recent work. Uses Gaussian mixture model, which is, and then it keeps updating again, gets an estimate of background, keeps updating the Gaussian mixture model, which I would think computationally is not too much faster than updating subspace. especially given now the recent work on there is also some. So we use SVD for subspace estimation or subspace updates, etc. But and we need only a few group or faster methods for SVD subspace estimation, which could potentially be used.
So what the complexity is that will?
Complexity, you mean order complexity or speed? Whatever is the complexity of SVD, which is I guess nr squared maybe. N is the image size and r would be the rank. Nr square, nr cube, roughly that much. In terms of time taken, I can pull out a paper and show you a table. Here. Here. So for an image size that's 120 cross 160, which is not very big, and this much length sequence, replots needed about 43 seconds, 44 seconds. So it's about 6 to 7 frames per second, which is not too fast, but not too bad. Compared with
what is a plus second?
Oh, plus, so this is the initial, so these were the not training, these are the training lengths. We used 200 frames for estimating the background subspace. That took 0.46 seconds, and the test part was much faster because you're doing a smaller sized SVD. The complexity is governed not by L1 minimization but by SVD.
So 42 seconds per frame?
For 42 seconds or 52 frames. So that's done. That's more like 1 frame per second. The first one, because it was a smaller sequence, was more like 19 seconds, 20 seconds for an 80 frame, 80 length frame. So not 2. It's between, I should say, 2 to 7 frames per second. Yeah.
Classical basic technique, they do like milliseconds. Yes.
Good.
Yeah.
Good. Then the ours doesn't go there at all. So, yeah. And again, even in the paper we wrote, the comparisons are with robust PC-based techniques, which are slower because they're very. And it's been on my to-do list to do exactly what you said. Go look at some of Object or OpenCV and its algorithms. But we just haven't done that yet. Any questions?
I'm wondering, you just show us some bound results. I'm wondering, the bound results is obtained when the algorithm goes to time infinity. How about the convergence speed?
Say that again?
Yeah.
What is it?
The result is a convergence result. The bound result is a convergent result.
It's not a convergence result. No, it just says
It's
that
for every time instant
for every time.
discovery.
Yes, very. Yeah, it says that under all these assumptions, the support is exactly recovered at all times. The error of xt and rt is small at all times. There is a value for the
So the bound holds for every time instant.
for every time, all times, at all times. Yeah, very much. And this says because of the model I assume on subspace change, where I say the subspace changes at a certain times, then remains constant for a while, then again changes.
Okay, great.
This obviously this reduces to a small constant within a short delay.
Another question is, robust PCR assumes the observation is a noisy linear measurement of the no dimensional subspace, right? How about to couple with the nonlinear measurement of the no dimensional subspace?
Also, if you don't have linear measurements but non-linear measurements of the coordination sections, you could, a first attempt I would think would be to linearize and do a linearized type of approximation. I have not looked into it so far.
So the results are mainly applied in linear measurement of.
Oh, the theorem, yeah, as far as I know, all results are only for the linear case. So linear as in, yeah, the observation is
Linear.
L sub t plus x sub t, yeah, linear, sorry. Or a linear combination will work too. A times x sub t plus b times L sub t will work too.
Okay.
Suppose now that you look at your problem in a bus fashion, so you have finished your
Sorry?
You have things you run.
Okay.
Look at the batch thing. Suppose you are in a regime that you have errors. You are not doing exact recovery. And you have, let's say, attained your low rank thing, your low rank matrix. Then you would like this matrix to have the smallest number of errors per in entry fashion from the true one, or you would like to minimize the distance of this matrix that you obtain from the true one in a Frobenius nonsense, for example.
So that again,
I mean, in these applications that you look at,
Mm-hmm.
in the end, what matters is the distance that the low-rank subspace has from the true one in Frobenius nonsense, or you would like to measure to count, let's say, how many errors you have per average. Because
The subspace error, the way I look at it is this distance. This distance. And 2 here, 2 is the Frobenius, this is the induced to number.
yeah,
So this is the, if P is the basis matrix for the true subspace and P hat is the basis matrix for the estimated subspace, I say take P, project perpendicular to P hat, and then look at the 2 norm of the resulting matrix. I think there's a term for that. Is this, I'm not exactly sure, is this called the principal angle? I think this is called the principal angle between subspaces.
Yes.
Right? Yeah. We just started using this because this was the most natural thing and this is what sine theta theorem wants. And then we realized that this is the standard metric, which is, yeah, it's called the principal angle between subspaces. So that's what we've done. P hat, actually, P hat T minus PT is, I think, very closely related to this. The Frobenius, not the Frobenius, no. The 2 norm between P hat T and PT is closely related to this. The Frobenius norm would be square root 2 or that would be used 1 to Frobenius norm.
Good, we're past time anyway. Thank you
All
very
right.
much.
And let me repeat that Professor Wani is here for the whole semester in
156.
56 CSL, so please stop by if you have any questions.
Or, of course, if you know my name, you can find my address.
Yes. Okay.